In this lecture, I'll review the measurement basics that you should be aware of, as well as simple data manipulations related to analytical chemistry. And we've already said analytical chemistry is a chemistry of measurement, and so it's very critical that you pay attention to the units, of chemical concentrations. In this lecture, we're also going to talk about preparing standard chemical solutions, of known concentrations. We're also going to comment, about stoichiometric calculations related to gravimetric analysis, which you've already started doing in the lab. You remember yesterday, you were doing the balance exercises, which refer to gravimetric analysis, and that's what you are doing in the lab. Now, may I emphasize that units are critical, and so anytime you do a calculation, you always have to have the units. Maybe let me start, with fairly costly faulty units. That happened a couple of years ago in 1999. Where you've got this Mars climate orbiter priced at 125 million that got lost, and the problem was very simple. It was a unit problem. Engineers built this spacecraft and they calculated the thrust needed using English unit pounds of force. Now, the other engineers, the propulsion lab engineers, used the metric unit newtons, to calculate the thrust that is needed. Now, nobody caught, the error, and after the orbiter was launched into the space, it was instructed to enter the Martian atmosphere 100 kilometers lower than it was planned, and as such the mission did not work, and the problem are the units. Now, in chemistry, we are often dealing with very small concentrations, and so the standard unit, sometimes we use prefixes because of those very small concentrations that we are dealing with. Sometimes we deal with deciliters, 10 to the power minus 1. We deal with centiliters, 10 to the power minus 2. Sometimes we deal with nanoliters, 10 to the power minus 9, and so on. And so you're going to find us using this type of prefixes fairly often. In some cases, you also use very large numbers, when you're talking, for example, about Avogadro's number of particles. We all of us know that 1 mole of any chemical substance consists of 6 times 10 to the power 23 Avogadro's number of particles. They can be atoms, they can be molecules, and so forth. So again, we use prefixes, because of the small or large type of numbers that we are dealing with. Now, as far as stoichiometry is concerned, I expect you guys remember and know what mole stands for, and mole stands for Avogadro's number of particles of any chemical species, whether an atom or a molecule. Atomic mass, refers to the number of grams of an element, containing the Avogadro's number of atoms. Now, molecular mass refers to the atomic masses of atoms that represent the type of molecule that one is talking about. And formula mass is very similar to molecular mass. It's only used largely to emphasize if the chemical entity is an electrolyte. And all of us know what an electrolyte is. It dissociates. Strong electrolytes, they dissociate completely into their component species, whereas weak electrolytes, only partially dissociate. So when you're dealing with strong electrolytes, we use the term formula mass as the composition of the atomic masses, of that molecule. When we are calculating concentrations, I think most of us are familiar, with the term molarity, which is the most common method of calculating concentration, which refers to the number of moles of a substance, a chemical substance, per liter. Another term that may not be very familiar to most of us is what they call molality, with a small m as a symbol. And in this case, you've got the number of moles of the chemical entity, but instead of liters, now you use kilogram of the solvent. So it's the number of moles, divided by the kilogram of the solvent used to make that solution. Now, you would wonder, why would we need to differentiate, these two types of methods or units of calculating concentration? Take note of this. The molarity, is volume dependent, and volume is dependent on temperature. If at all you're in a warm place, solvents tend to expand, and so the volume will be different. And so in that case, the molarity is going to be different. So if you're in Hawaii or Arizona, very hot temperatures, and you measure something and represent it in molarity, that molar concentration would be different than if you go to a very cold place, such as the Arctic. For that reason, sometimes we use molarity with a small m, because the concentration is temperature independent. You're dealing with masses in kilogram, and so that is temperature independent, and so it doesn't vary, with temperature. As I've said before, the formal concentration, is only used to represent molarity, for chemical species that dissociate, completely to their component species. Now, that's not always the case if at all you're dealing with weak acids or bases, that tend to dissociate only partially. Okay. And we're going to talk about later on, a lot about, weak acids, that only dissociate partially. But again, I emphasize the formal concentration F is the molarity of a substance if it were not converted to other chemical species. So it is mainly used, for strong electrolytes. Now, I'll give you a quick example just to jog your brains, about calculating molarity, which I think you all know about it, but just to make sure we are on the same page. Assume you're given a problem like this, typical seawater containing 2.7 grams of sodium chloride, and it was dissolved in 100 ml or 0.1 liters. How do you calculate the molarity or molar concentration? You just need to get the formula mass, which are the component species that are present. The atomic weight or mass of sodium is 23. The atomic weight of chloride is 35.45. And you combine them up to get the molar mass, which is 58.44. Now, the number of moles we all know is the grams of the solute divided by the molar mass. And so the number of moles are calculated there. Then the concentration would be the number of moles divided by the volume. And of course, the volume, we said it's 100 mils. And so the concentration is 0.46 molar concentration. In some cases, you know the concentration in molar concentration. Say in this case of magnesium chloride, you've been given the molar concentration and you want to know how much solute you need to weigh. And so in that case, you know the volume, say, of the volumetric flask, you know the concentration that you want. And now what you need to do is take the molar concentration in moles per liter multiplied by the molar mass of the solid, which is calculated there. And then you get the grams, and then you get the grams. And of course, you need to multiply it, you know, by the volume in liters. You know, so you take again the molar concentration multiplied by the molar mass, then you multiply by the volume in liters, then you're going to get the answer in grams. It's very important to keep the units when you're doing the calculation so that they can cancel out, and that way you're able to track what the final units would be. Now you can also represent concentration in form of percent composition, and you can do it in two ways: either weight percent, you know, which is the mass of the solid divided by the mass of the solution, you know, times 100. And so this one is gonna be in grams per gram. So that's the mass of the solute in grams, you know, the mass of the total solution, which is a solute, you know, plus the solvent multiplied by 100. And so sometimes you would call it, you know, weight percent, as in like sometimes people would represent it, you know, like that. Now, the other type of percent is a volume percent, which is the volume of the solid divided by the volume of the solution, which is a solid plus a solvent, times 100. And so sometimes people will represent it, you know, as volume percent. Now, it's possible to convert between the weight percent into, you know, molarity or even molality. It's possible to do that. I'll give you an example in this case where you're given weight percent of hydrochloric acid. There's 37 weight percent, you know, which is gram per gram. And in this case, you've been given the density. Knowing the density, you can calculate the mass that is present. So you take, you know, the weight percent, and the weight percent means 37 divided by 100, you know, that's grams, you know, that's grams, and that's how we got this number, the weight percent. And then you multiply it by the density. And if you multiply by the density, you're gonna get the mass per volume. That's what you have there, mass per volume. And knowing now the mass per volume, you can calculate the molarity just by dividing this, you know, with the molar mass, with the molar mass, you know, which is down here. The molar mass of HCl is 36.46, which you get, of course, from the periodic table. You know, hydrogen is around 1 grams per mole. Chloride is 35.5 grams per mole. You combine the two, you know, and then you get that number. And that's how you get the molarity of 37, you know, percent of HCl. So that way you can convert between percent and molar concentration. On the other hand, if you're looking for molality, you know, remember this refers to moles per kilogram of the solvent, per kilogram of the solvent. Now, what you need to do is take, you know, the weight percent, which is 37 grams in 100 grams of solvent and water. So you can see the amount of water that is present would be the 37 you know, grams of HCl, and then the rest is gonna be water. And so the water in this case is gonna be 63 grams, and you have to convert it into kilograms to get 0.063. Then after that, you can calculate the number of moles of HCl. We already know that there's 37 grams of HCl in 37% weight percent. And then you need to divide that by the molar mass. And we know the molar mass is 36.46. And that way now you've got the number of moles. And knowing down the number of moles, you can divide it by the kilogram of the solvent to get the answer in molality, the small m. So take note of the difference in the calculation between molality and molarity, the capital M. Maybe at home you guys can do this problem, calculate the molarity, the molar concentration, which is moles per liter. And then also calculate the molality for that problem, which is moles, per kilogram of the solvent. Okay, and I hope it's fairly clear in this case. The grams that are present is 32.6 grams are present, and 100 minus 32.6, those would be the grams of the solvent. And then you convert this, you convert that into kilogram, and then that way you're gonna get the number of moles. So you're gonna get the molality. Yeah, you're gonna get the molarity. And of course, this one you're gonna need to divide it, by the molar mass, Yeah, nonetheless, do that problem at home. If you've got a challenge, let me know. Now, it's important to remember the importance of doing this. When you get a reagent from the manufacturer, in most cases, they have it, in percent. And so you need to convert it, to the molar concentration in the way that I've shown you. And all what you need to know is that the weight percent, so long as you have the density, then you can convert weight percent into molarity. As I've said before, the weight percent, sometimes you're dealing with very, very small type of concentrations. And so sometimes we use these terms such as parts per million. Now remember previously, if at all I have this, and I multiply it by 100, that's percent composition. Sometimes at all you're dealing with very, very small amounts, then sometimes you're dealing with parts, so-called parts per million, or the ppm, which refers to the ratio of the substance, to the sample multiplied by 10 to the power 6. Sometimes we can also have the parts per billion, which means the gram to gram, that's the mass of the substance, divided by the mass of the sample times 10 to the power 9. Now you can convert, these sort of mass by mass, into volume just by multiplying it, with the density. Remember, the density of most solutions that are made with water is very, very close to 1. And so if you multiply by the density here, which is 1 gram per mil, then you can convert, the ppm into mass by volume. So the definition of ppm in mass to volume is milligrams, per liter, or microgram, per mil. On the other hand, parts per billion into mass by volume is nanogram per mil, or microgram, per liter. So take note of sort of, those, definitions of parts per million, parts per billion, which is very, very common in analytical chemistry. Now, what if I give you a problem like this, where I've got a hydrocarbon in parts per billion, and then I ask you to convert that into, into molarity, which is moles per liter. Now, knowing the definition of parts per billion as nanogram per mil, or micrograms per liter, so 34 micrograms per liter, all I need to do is to divide the microgram per liter, with the molar mass of the hydrocarbon, in this case, which is 408.8 grams per mole. The grams cancel out, and so the answer is going to be in moles per liter, which is a molarity. So take note of the conversions between parts per billion into moles per liter. Maybe another simple problem here: convert the molarity of this fluoride solution into parts per million. Again, what I need to do is multiply that number, by the atomic mass, which is grams per mole of fluoride, and then I'm gonna get, the answer in grams per liter, and then after that, I can multiply by 1,000, to get me the milligrams, per liter, which is the definition, of parts per million. So take note of those simple conversions. Maybe if I can summarize very easily, if at all I give you a problem like this, where you've been given 6 molar of nitric acid, okay, and you've been asked to make 100 mils of 1% nitric acid, okay, from the 6 molar concentration. How do you do that? How much of the 6 molar do you actually pipette, into the 100 ml volumetric flask? So you need to convert, this molar concentration into percent so that you can do the dilution. Maybe I'll show you a very simple formula of doing it, where you've got, this percent is equals to the molar mass times the molar concentration divided by the 10 times the density in grams per mil. And I've tried to derive that relationship here. So the 6 molar, you can convert it to percent, okay? But just by substituting that equation. And then after that, knowing that the 6 molar is equivalent to 26.62%, you can do the dilution using the dilution formula, which I believe you guys know about it, so the CV is equals to the C1V1 is equal to C2V2, which you guys know about. So you need to pipette 3.76 mils of the 6 molar, which is equivalent to this, in order to make 1% of 100 mil of nitric acid. So pay attention, to these kinds of conversions. So I've just explained, how you prepare a solution with the desired molarity, and typically what you do is you would take the solid, you weigh out the mass of the reagent that you need, and you dissolve it, in the volumetric flask, often using the deionized water. In some cases, you can use the distilled water, but in most cases, you use the deionized water. The deionized water means all the ions, have been removed from the water whereas distilled water just means, you've just distilled the water, the ions, still remain. So maybe, a problem like this one, which is something that you can come across in the lab. Now, you've been asked to prepare a standard solution of 8 millimolar, of copper ions, and you've been given the salt, the copper sulfate pentahydrate. So how do you do that? And you've been asked to make 500 mils of that 8 millimolar solution. So remember what you need to do, is take the 8 millimolar, of course, convert it into moles per liter. That's what I'm multiplying by, dividing it by 1,000 there, moles per liter. Multiply that, by the volume so that you get the number of moles that you need, okay? And then multiply that by the molar mass of the salt, which is given there, and you get the mass that you need to weigh. And so you weigh that using the analytical balance like you've already done, and then you dissolve it with a small volume of distilled water, swirling it, until all the salt has been dissolved. And then after that, you can dilute it to volume, on the mark. And that's how typically you would prepare a standard solution. If you've been asked, to do a dilution of that standard solution, again, you use the dilution formula that you guys are aware of, the molar concentration of the concentrated solution, the V1, maybe often you don't know what this one is, so that's what you'll be looking for, the concentration of the dilute solution that you hope to get. And the volume of the volumetric flask, and so based on that relationship you can take an aliquot of the concentrated solution, put it in the volumetric flask and make it up to volume. In the lab this week you already did the calibration of the pipette, and I think you were introduced to the idea that whatever you get on the analytical balance is actually an apparent mass, and because the apparent mass always has got the buoyancy due to the lifting of the analytical balance due to the air force that is lifting the analytical balance. And so you need to multiply with that buoyancy correction factor to get the true mass, and then after that you can divide it by the density so that you can get the true volume, and you guys did that already. Maybe the only thing that I like to emphasize is the following. In the event, you get the temperature of your water, being somewhere in between, maybe two temperatures, maybe two values where you don't actually know the density, like the density at 24, the density at 25, but maybe the temperature of your water is 24.7, you would do the so-called interpolation as shown in this relationship here. And I think some of you, I already showed you how to do that. That's how you do the interpolation, to get the density at the exact temperature. So you don't round up, you don't round down, you do the interpolation, as I have shown here. Okay, and then that way you can get the concentration of your calibrated, the volume of your calibrated pipette. And so then the next lecture that I'm gonna give, is gonna be about experimental error. But I assume what I've covered is sort of what you already know, but I'd like you to revisit that.